Hello everyone, and thank you for attending today's webinar, Crystallographic and Strain Mapping in Beam-Sensitive Halide Perovskite Thin Films. Before we begin, I'd like to cover a few housekeeping items. At the bottom of your audience console are several application widgets. These widgets can be used to do a number of things. First, you'll have the questions you can ask during the webinar. If you click on the Q&A widget and submit your question, please direct your questions to a specific speaker you want to answer from. We'll try to answer these during the webcast, but if a fuller answer is needed or we run out of time, you'll receive an answer later via email. We do capture all of your questions. A copy of today's slide deck is available in the resource list widget. It looks like a green folder. You can expand your slide area by clicking on the maximize icon in the top right or by dragging the bottom right corner of your slide area. If you have any technical difficulty, please click on the help widget. It has a question mark icon and covers common technical issues. An on-demand version of the webcast will be available approximately 1 day after the webcast and can be accessed using the same audience link that you used to access the webinar today. Now I'd like to introduce the presenters for today's webinar. Matt Nall is the EBSD product manager at EDAX and has a passion for EBSD and microstructural characterization. Matt joined TechSem Labs, also known as TSL, upon graduation from the University of Utah in 1995 with a degree in materials science and engineering. At TSL, he was part of the team that pioneered the development and commercialization of EBSD and OIM. After EDAX acquired TSL in 1999, he joined the applications group to help continue to develop EBSD as a technique and integrate structural information with chemical information collected using EDS. Within EDAX, Matt has held several roles, including product management, business development, customer and technical support, engineering, and application support and development. Matt has published over 70 papers in a variety of application areas. He greatly enjoys the opportunity to interact with scientists, engineers, and microscopists to help expand the role that EBSD plays in materials characterization. Our second speaker is Loretta Muscarella. She's a PhD candidate working at AMOF in Amsterdam. She works in the hybrid solar cells group under the supervision of Professor Bruno Ehler. She obtained her bachelor's and master's degrees in physical chemistry from La Sapienza University of Rome. Her research expertise is the strain effects on halide perovskites and how external stimuli or internal strain can affect the properties of such materials. The third speaker is Hongyu Sun. He's also a PhD candidate working at AMOF in Amsterdam. He works in the nanoscale solar cells group under the supervision of Professor Dr. Eric Garnett. Hongyu obtained his master's degree from the University of Amsterdam and a bachelor's degree from Beijing Institute of Technology. He focuses on the characterization of halide perovskite thin films via EBSD and fabrication of back contact perovskite solar cells. Now over to Matt.
Thanks, Jonathan, for that wonderful introduction. And I'm very excited to be here with Loretta and Hongyu today to talk about characterizing and understanding these perovskite solar cell materials. So from my side, I'm going to talk a little bit about microstructure and EBSD, or electron backscatter diffraction. Then I'm going to introduce a direct detector, Clarity, which is used for characterizing these materials. I'll try to explain why. And then I'm going to give just a quick application example of using this detector on some perovskite solar cells materials. And then I'll turn it over to the AMOF group. I'd like to acknowledge the help from my coworkers, Renee DeClos and Stuart Wright, on a lot of what I'm going to present. Also like to acknowledge the University of North Carolina providing the samples that I'll show. So what is microstructure? You know, people who look at perovskite films come from a couple of different directions, but conventionally we think of microstructure in terms of things like grain size and shape, chemistry, phases. And from an EBSD perspective, the information that's missing is crystallographic orientation. And then when you have different crystals coming together, we end up with grain boundaries or crystallographic misorientations. And so that's the information that EBSD starts to bring to the table when we talk about characterization. So why do we care about crystallographic orientation? the key reason is anisotropy. The properties of materials can vary with crystallographic orientation. So as an analogy, I have a little cartoon here where we show a piece of wood where the grain of the wood is oriented on the top there in a weak direction, on the bottom there in what would be a strong direction or strong orientation. So if a force was pushed to try to break that piece of wood, the orientation would affect the amount of load needed to break that piece of wood. And that same idea applies to crystals in materials, that your properties can vary with crystal orientation. And so the joke I always have is when I learned this in school, we said it all averages out though, and everything's isotropic, and we worry about anisotropy later. Well, for me, later's here, and most materials, when they're formed, will form some degree of what's termed preferred orientation or texture. And that's just to the energy minimization effects that comes when we deposit films or when we deform a material, we solidify things. And so what we do with EBSD is we try to look to say, are crystals randomly oriented? Is it a single crystal? Or what it is between those two regimes? Is it a polycrystal where grains are all aligned in one direction or they're aligned in all directions? So EBSD allows us to do this spatially specific point-by-point mapping where we can recreate maps showing how different grains are oriented. The other thing that's important, like I mentioned, are grain boundaries. What happens when these two different orientations come together? So the top right chart here shows a chart from a textbook where it's grain boundary energy versus misorientation. So when you have two orientations that are just a little bit different, it can kind of be described as a line of dislocation of the material causing small low angle rotations. And as the misorientation between those points becomes greater, the grain boundary energy becomes up because your dislocation density is higher to cause that amount of misorientation. As it transitions to what's shown as a high angle boundary, though, we end up with a disordered grain boundary transition zone. So your grain boundaries change a little bit as a function of misorientation, but not all high angle misorientations have the same grain boundary energy. And that's what I'm trying to show on the bottom right here, that for some crystals, there are specific misorientation relationships. And that means there's a specific axis of rotation and angle of rotation that have a minimization of energy. And those are what are called special boundaries. I put special in quotation. But sometimes it's twin boundaries in materials. Sometimes they're described by what's called a coincident site lattice model boundary type. But the key thing is those boundaries will have different properties than random high angle boundaries. And EBSD is a good tool to identify those specific type of boundaries. So EBSD, first of all, if you're not familiar with it, it's an SEM-based characterization technique. And so we have a crystal. It works on crystalline materials. We fire the electron beam into a specific point on the sample, so it's a spot-based technique. Within that spot, it interacts with the unit cell as shown there, and the beam generates basically a virtual point source that acts with the different crystallographic planes in the material. This cartoon shows one specific plane here. It diffracts. That diffraction goes out towards the detector, is captured by the detector, and each plane is essentially represented by a line or a band in the EBSD pattern. So the array of those band positions tells us how the crystallographic planes are aligned in the material. We measure the angles and positions of those planes. That determines the crystallographic orientation. What we do with what we call OIM, or orientation imaging microscopy, is automated EBSD mapping. So we couple our detector to the computer, we specify the area of interest, we specify the step size, and at each point we capture this diffraction pattern. We analyze it with image processing to determine the position of these diffraction planes, then determine the crystallographic orientation, and also typically the phase. And so at each point we end up with that information, as well as a number of other metrics. And once we have that, there's a number of different things we can do. So this cartoon kind of shows we can create a bunch of different maps. We can quantify the microstructure in terms of charts, and we can analyze that orientation distribution and preferred orientation distribution. So we get information about orientations, texture, grain boundary character, grain size and shape, local changes in orientation, phases. We can also correlate this with other signals like chemistry, where we can collect EBS data, or other signals like cathodoluminescence, and see how those signals and information correspond with the EBSD data. And of course, this is key idea in material sciences. You know, we want to have this information to understand the link between how we process a material and the properties we get, and how the processing influences the microstructure. So being able to characterize that provides important information to understand things. So the driving force for this particular topic, of course, is that, you know, there's a strong need for alternative energy sources in the world. There's a growing demand for energy, and this demand drives new materials and new technologies for energy generation and storage. And so solar power through photovoltaic devices is one sustainable source of alternative energy that has attracted a lot of attention for development for a number of different material systems. So I've been involved with looking at different solar materials for probably about 15 years now. EBSD was originally used in silicon solar cells. In silicon, single crystal devices have higher efficiency. So they're not very exciting for EBSD. You kind of get one orientation and one grain. But to reduce cost for polysilicon, they went to polysilicon. It's less efficient but less expensive, and then understanding the roles of grain boundaries and twins become important. In other materials like CAD-TEL or SIGs, these polycrystalline films have had higher efficiencies. So trying to understand the role that the grain boundaries play in affecting efficiencies was an important area of research. And then, of course, recognizing for all these different photovoltaic materials, the microstructures are generally not randomly oriented and have some degree of texturing. And so wanting to correlate that to performance. And so for this, we wanted to ask, what role does the microstructure play in other PV materials and applications? So this is just an example. Again, grain boundaries are often a new concept for people not familiar with EBSD and understanding how the varying grain boundary character can influence material. This is just an example where the EBSD map there on the bottom, the special grain boundaries or the twin boundaries are shown in red, and the CL signal there from the same area is shown on the top. And you can see that the red boundaries do not have a decrease in CL intensity. So they're not degrading the performance of the CL signal. This is work from Abu Ras from a few years ago, but it shows how you can correlate electrical characterization measurements directly with the EBSD results. So the focus of this webinar is on perovskite solar cells, and I'm just going to give a very brief introduction. You know, perovskite's a general term. It's named after a mineral with a very specific crystal structure. As solar cell materials, they're showing good potential for high performance, low manufacturing metrics, and rapid improvements of efficiency have been reported. But there's still challenges that remain for improving the efficiency and stability of these materials. And so to achieve both of those things, we need the capability to characterize the microstructure to help understand and improve the efficiency and stability. So just to kind of show the growth of this is something I pulled off of Science Direct, just using perovskite as a keyword. Just shows the number of publications in about the last 10 years and how it's grown significantly in terms of research interest. And so, you know, as we've looked at these, of course, we've seen a number of groups that have said, hey, we're interested in using EBSD to characterize these perovskite cells. And we've seen a wide variety of different microstructures. And so these are just a few different examples where we see, you know, microstructures that are you know, at least made up of a set of different components. So we see some that have smooth grains, some that have contoured faceted grains. One, if you look at the top right, there are grains that I've kind of described as coral grains. They kind of have some porosity built into them. There's ones that have brighter particles and brighter plates. But we do observe a grain structure. But what I want to point out is in the bottom right image, you'll kind of see about somewhere between 1/2 to 2/3 of the way through to the right, there's a vertical line. And on the left-hand side, before this image was taken, that area had been imaged previously. And then I took another image where I got part of the image that had been imaged previously with a fresh area. And you can see on the left of that, there's some gaps between the grains. We've seen a change in the microstructure due to the beam exposure from imaging the sample. So these films can be extremely sensitive to beam damage during characterization, and you can actually observe this. So, you know, the best results are seen at very low beam currents, 10 to 100 picoamps, to be able to characterize these materials. So to be able to characterize these, we need very high sensitivity for our EBSD detector. So that leads us to the detector that's been used for this webinar, the work in this webinar, which is the Clarity Direct Detector. It's the first direct detector designed specifically for EBSD. And of course, when you're bringing new technology, that means we're opening new applications, and we're pushing to use these on the variety of different perovskite solar cells. You know, as a direct detector, it gets rid of phosphor screens and optical couplings that are used in traditional detectors. So we get very nice patterns, we can get high dynamic range, but the important thing for this application is it has very high sensitivity. There's no read noise, so we can go to very low beam doses and still extract usable EBSD patterns. So as a little schematic of how this detector works, it's what's called a hybrid pixel direct detector. So this is a schematic of the detector here on the left. The sensing materials on the top, it's bump bonded down to the readout circuitry. So when the electron hits the sensor, it generates a charge. That charge is then drawn into the amplifier where it's amplified. There's thresholding that goes on to remove the low-end noise. It's essentially similar to a discriminator in an EDS detector. And then once that's done, it basically counts electron interaction events. And so basically that means we can detect single electron events with a detector. That allows us to run at very low beam currents. So the thing with EBSD to understand that I want to emphasize is that the EBSD signal itself, though, is a complex signal. So the image on the left here is a live signal from the detector, but we're looking at multiple grains. So the orientation information is averaged out, and the horizontal line going through there is just showing the intensity profile across the detector. So you can see it's a non-uniform illumination. It's brighter in the center, and it tails off towards the edge. And then when we put the beam into a spot mode into an individual grain, that's when we see a diffraction pattern like we see on the top right there. And if we look at that same intensity profile, you'll see that the diffraction information is superimposed across that background signal. So while we get single electron sensitivity, we often have to detect more than one electron to be able to extract the diffraction information over what I call the scattering information. And so this is just an example showing this effect. So this is a pattern here on the left where we've collected a lot of electrons, 5,000 on average. So like I mentioned, on average, there's more in the center, there's fewer on the edges, but 5,000 on average. And if we look at that same line profile after background subtraction, there's a lot of dynamic range available within that image. We get high contrast, it's very pretty. The second image there, we're dealing with only 10 average electrons. So a lot fewer electrons available for the signal, but if you look at it, you can actually see there's a diffraction image. You can see on the right, we're able to index that image, even with that sparse of a sampling acquisition. And so what that means is we can go to very low conditions and work with very few number of electrons and still get usable results. This is a result showing where we're mapping at that 10 electrons per pixel on average. This is at 13 picoamps on a stainless steel 3D printed material, but you can see we get very nice orientation information. The black points there, the points that are not indexed with high confidence, you can see they correspond to pieces of dust and grain boundaries. And the grain boundaries often are where you can have mixed patterns that are you know, when you have fewer signals, you don't have enough information to resolve one signal versus the other. And so this clarity performance, it can go down to very low you know, number of electron doses. It also has higher sensitivity at beam voltages, and the sensitivity improves as the voltage decreases. So this is just kind of showing, how the difference between a phosphor-based detector and a direct detector changes as the voltage decreases. So this is what we call our Clarity Plus that has, performance down to about 6 or 7 kV. We also have the Clarity Super, which is a new improvement where we've improved the sensitivity down to 2 or 3 kV with significant improvements at those lower voltage range. So the reason that lower voltage is important is, one, it can reduce the energy, of course, of the electron, so it can minimize damage. It can also improve the spatial resolution. So this is just a little schematic here of sort of an estimate of the spatial resolution improvement in terms of interaction volume at 2 different voltages, so 20 kV and 5 kV, on 3 different materials. So the reason 3 different materials are important, the lower the average atomic number of a material we're looking at, the greater the mean free path between electron interaction events during the electron beam sample interaction. You'll also see I've put things here different in terms of X and Y directions on the sample. The reason that is of course, for EBSD, I probably didn't mention, we tilt the sample to around 70 degrees. So we get better spatial resolution sort of along the tilt axis rather than down the tilt direction. But still, reducing the voltage gives a significant improvement, somewhere around 3 to 4 times improvement in the X direction, 4 to 5 times improvement in the Y direction. And so that opens some interesting new doors for looking at smaller grain materials at lower energies. This is an example. It's a methyl ammonium lead iodide film. Certainly, we've looked at a lot of materials. The first level thing of being told it's a perovskite solar cell doesn't really limit down the exact materials that are used. There's a wide range of materials with a wide degree of beam sensitivity. These ones were pretty beam sensitive. The best imagings were collected at 8 kV and 50 picoamps and 20 picoamps in low vacuum condition. So, even with the clarity, these can be a little challenging. But what you'll see with the microstructures, you can see a grain structure, a little bit of porosity, and then you see these brighter platelets that are growing out of some of the grains. And you can see just from the images that there's some preferred alignment of these platelets relative to the grain structure. The other thing that's important for EBSD, if we show this now, this is the same sample here on the left. We're looking at it in a normal imaging condition. On the right, we're tilting it to 70 degrees for EBSD. And so you can see there's some pretty significant topography with the material. And so what that means is if we put the beam in different points on these grains, as the beam interacts with material, only some fraction of those points generate patterns that have line of sight towards the detector without being absorbed or blocked by other parts of the material. So traditionally for EBSD, you'll do some sort of mechanical or ion polish to try to make these pretty flat. These materials really aren't conducive to a lot of that type of preparation. And so we just have to deal with the topography. And there's some things we can do to try to improve on the band detection and image processing for these type of things. And I'm going to show one trick that we do for these materials. But this just kind of shows one quick map. This is a small area map. Looking at it, I put here no NPAR. That's an approach I'm going to explain. But basically, without NPAR, we're looking at the patterns here. You can see we're at 10 kV, 40 picoamps. And we're getting patterns from the brighter particles, which are the lead halide particles. When we apply NPAR, you'll see that the colored points here grow out. And we start to get signal from the underlying grains as well as the brighter particles. And what that shows, and I'll show again if I go back and forth, is that I mentioned those platelets have an alignment with the grains. It's a preferred growth of those platelets off of the grains, or at least a similar orientation relationship. And so with NPAR, what we're doing is we're doing what's called local pattern averaging and re-indexing, and that improves the signal to noise of the pattern. And so basically what we do is we save all the patterns, and then we average one point with the patterns around it to improve the signal to noise for these parts of the grains that have weaker diffraction relative to the lead iodide particles. So we can show this for a larger area, and you can see we start to see the orientations of all those grains come out. And then we can look at the orientation distribution. So you'll see here, these are pole figures. So this is showing the position of the 001 crystal planes. The center is the surface normal direction, and the A1 and A2 directions are different directions within the microscope reference frame. You can see the discrete plots there, which are the black dotted parts, especially for the larger grains, we have a lot of information. So this is where we create these density plots here, these color plots, where we fit functions that describe the positions of the orientations and the strength of those particular orientations. So what we can see here is that the 111 pole figure, the bottom one here on the bottom right of each one, there's a peak in there. It's showing there's a preferred 111 orientation for both the larger grains and the smaller grains, showing that sort of an epitaxial type of a relationship between the two microstructural components. So from my side, I just wanted to summarize that these perovskite solar cells are exciting new materials for renewable energy applications. They can be challenging to characterize at traditional SEM conditions. The Clarity direct detector uses next generation technology to provide the highest level of sensitivity for these low beam dose applications, can offer high performance at both low beam currents and low beam energies. And this offers improved characterization on these organic, inorganic perovskite solar materials. So with that, I am going to hand it off to Loretta.
Thank you, Matt. Hello, everyone. Thank you for attending this webinar. In this second part of the talk, I will introduce first the work that we are going to present together with the OnView. I will focus mainly on the effect of crystal orientation and grain size and how this correlates with the optoelectronic properties of methylammonium lead iodide. And then I will give the floor to OnView, who will talk about local crystal misorientation and how this can influence non-radiative recombination in halide perovskite. So to start, I would just like to spend a few words on perovskite. Already Matt introduced a bit this very interesting and challenging class of materials. So you can see here the crystal structure of a typical perovskite with the formula ABX3. So the perovskite is made of repetition of octahedra, where in the middle we have a bivalent cation, which is in this case lead 2+, and this coordinates 6 halides, in this case iodide. And in the middle we have a monovalent cation, which can be either organic or inorganic. And in this talk I will focus on the organic monovalent cation, which is the methylammonium. So the reason why these perovskites are so promising material for many applications, so not only PV, but also LEDs, photodetectors, and so on, is that they show very peculiar and interesting properties. For example, high absorption coefficient and high mobility, but also the long charge lifetime. These are some properties that are very desired for solar cell application, but on the other hand, they also show high PLQI, which is very interesting for making LEDs, and the fact that they can have a very easy band gap tunability. So that means that we can obtain anything in between, for example, the near infrared and the visible, but just by changing the halide ratio in the composition, makes them really unique for making solar cell, tandem solar cell, LEDs, and so on. And they are also very easy to process, so just by solution, which also open for large-scale production. So if we just have a quick look to the solar cell performance, you can see that in the last 8 years, the efficiency of such solar cell based on perovskite have increased from 12% to almost 26%. So it's now it's 25.8%, and this makes them, of course, even more interesting as a material to study. So the problem with this perovskite is that, of course, the efficiency is going up quite quickly, but we also want to understand how we can improve even more this material. And one of the problems of solar cells is really the grain size. I say it's one of the problems because most of the time, so that if you have small grains, so you have also grain boundaries, and it is possible that these grain boundaries can act as non-radiative recombination centers. So that's the reason why in several groups are doing a lot of efforts in improving the grains and make large grains by using some chemical additives. And this is because the increase in the non-radiative recombination increase the voltage loss. So that means that your solar cell is less efficient. So so the goal of this project was to understand if actually making a solar cell with small and large grain was actually affecting the optoelectronic properties. So what we did, we focused on methylammonium lead iodide, but this time made with two different fabrication strategy. So on the left, you have the typical anti-solvent method. So the fabrication method that involves the anti-solvent is basically spin coating the precursor solution and introduce at some point during the spinning, during the deposition, the anti-solvent which catalyzes the crystallization. And on the other end, you have this FIRA method, which is flash infrared annealing. And the idea of this method is that you just spin coat your precursor solution, so you don't use the anti-solvent, and then you apply a short infrared pulse of light to induce the crystallization. So the result of the morphology of the film is shown in this slide, and you have on the left very small grain, so they are about 400 to 1 micron in size, and then on the right you can see that the size of the grains looks much larger. So it's about 700 micrometers. So what we saw is that when we make a solar cell out of these two samples, the efficiency was very similar. So what we did was to investigate the grain size with the EBSD. So as Matt said just before, the EBSD is an SEM-based technique where you have this primary beam, we have the sample tilted by 70 degrees, and then we can collect the backscattered electrons which undergo to diffraction. But the problem is that, of course, in conventional system, you need very high current to get a decent pattern. Also, you need to have long exposure time, and you need to prepare your sample, or you have to polish your sample. On the other end, we have the Clarity detector, which is the one that we have used for this specific project. And for this one, we really need low current. So the measurement that I'm going to show you are by using 50 picoamps and 100 picoamps as current and an exposure time of 50 milliseconds without sample preparation, which is great because the perovskite is quite sensitive. And the reason why this perovskite is so sensitive is has to be found in the especially on the organic part of the perovskite. So you see here from this image that already under the SEM, the perovskite is very sensitive. So you see before imaging, we have a very nice and homogeneous surface, but then after imaging, you see cracks in the film. And the reason for this is that the electron beam help the evaporation of the organics, and the progressive volume shrinkage results in the biaxial tensile stress. So that means that the perovskite break, so we have many cracks, and also the the material becomes less crystalline. So for this specific application, the Clarity detector was perfect because we don't have to use very high current. So what we did was to measure this big grain of that you have seen in the FIDA sample. So there was around 70 to 100 micrometer. And here you can see a typical EBSD, typical pattern that you can get from the EBSD. Of course, for those of you who are familiar with the EBSD and with and have worked, for example, with silicon, this might look much more noisy, but that's pretty good for a perovskite sample. So what we did was indeed measure the whole cluster and see whether this was a single grain. As you can see here, if we look along the X, Y, and Z direction, you can immediately see that there are mainly two orientations perpendicular to the substrate, so along the Z axis, which are the 112 and the 100, and these are also in agreement with XRD measurements that we have done on the same sample. But then along the X and Y axis, you have different colors which correspond to different crystallographic orientation. So from here, it's quite clear that this is not really one single grain, but there are many grains, and there are also some grain boundaries in between those small grain. And so then we can say that this is not really a grain, but we call it a cluster, which is made of many grain. So this is quite important because that means that not always what we see in the SEM is actually a crystallographic grain. So we should be very careful when we are imaging and talking about grain size with perovskite. What's nice about so then basically we performed the same experiment also on the anti-solvent, and what we found is that the grain size that the apparent grain size in the SEM is much larger compared to the real one. On the other hand, the reason why using this EBSD system is very nice for investigating this type of material is that you can actually correlate the structural properties with also specially resolved optoelectronic properties. For example, we can correlate the crystal orientation that we observe with the EBSD with the specially resolved PL measured on the same sample and on the same grain. And you see that here we do not see a direct correlation between crystallographic orientation and photoluminescence. So that means that a specific crystal orientation doesn't result in higher or lower photoluminescence, but also that the grain boundary that we find in the grain, they are not really detrimental for this sample. We do observe an increase, though, in the photoluminescence in the middle and at the edge, but this doesn't have to be attributed to the crystallographic orientation, but more to thickness and a self-absorption process. So, just to conclude, the main message of this my talk is that perovskites are very sensitive material that have to be measured also with a very sensitive tool, as for example the EBSD with this Clarity detector. But then we should not also trust too much the SEM image for these grains, because most of the time the real crystallographic grains are different than the grains that we observe in the SEM. And also EBSD is a very powerful technique, not only for structural information, but also to correlate structural information with other properties that a material can show. And this is, I think, is great about this technique. So with this, I would like to conclude, and I will give the floor to Ongyu for the second part, or the third part of the talk. Thank you.
Okay, thanks, Loretta. So here's Hongyu, and also thanks, Matt, for for organizing this nice webinar. So my name's Hong Yu Sun. So I'm a PhD student at AMOF, and during my PhD, I have done a lot of EBSD on perovskite thin films. So here today, I will share some of my experience and also some of the samples I measured before. And also I will explain a little bit what we can do with the EBSD and why do we need it for perovskite thin film, especially when we are talking about the solar cells. So the first thing I want to share with you is the beam damage on perovskite film. So in my experience, I measured a lot of different kinds of perovskite, so from 3D to 2D, and also we try a lot of tricks to limit the damage, and also try to get more nice clear Kikuchi patterns from the sample. So on the left side, you can see this result is from a 3D perovskite, massive ammonium light bromide, and you can see this sample is very stable. So we at the beginning it didn't work at all, but we tried a lot of things. So we tried a lot of different voltages, and we tried the different mounting techniques, and also we try to increase the conductivity by using different substrate, by putting the silver paste around the sample, around the film. And in the end, so we can see even with the 20 kV electron beam voltage, we get a very clear Kikuchi pattern from this sample. And so here we want to say, so basically the exposure time is very important. So perovskite is very sensitive, so we normally use the exposure time between 100 to 200 milliseconds. So lower than this amount, you cannot get enough electrons out of the film. So the pattern will be very, very dark. So it's not good for measurement. But above this this exposure time, then the film will be damaged. So that's still bad for the measurement. And we also tried a lot of 2D perovskite, but so far we didn't get any luck. So we tried this Ba2 lead iodide film. So it's kind of perovskite flakes, very large. So we expect it to be a single crystal. That's why we measured with the EBSD. And from SEM, you can see it's a very large crystal. But with this one, we couldn't get any signals. And every time we measure it, we can see this damage. You can see on the right side, right lower part of this slide. You can. So after the scanning, we always end up with this pits, this damage on the film. This is all from scanning, and we tried different current, voltage, but they all didn't work. We think the reason can be, first of all, the perovskite, the 2D perovskite is too sensitive to electron beam. This is also seen from other papers, and also maybe because of charging. So you can also see from these two images, after the scanning, the SEM area is actually moved a little bit down. And you can see, and we think this is because of the charging, the bad conductivity of this film. And another thing I want to share is film roughness sensitivity. So EBSD is very sensitive to the film roughness. You can see on the left side, so this we have this cesium lead bromide sample received from our collaborators, and there are two kinds of grains, two different morphologies, and there are some needle-shaped grains which are located around the middle area, and also we have some flakes on the left side and right side. If you look at the EBSD map, so in the middle, you can also see some needle-shaped green lines purple lines, which correspond to the needle-shaped grains in the SEM. And at the left part, you can see a very large purple grain, which corresponds to the flake on in the SEM. So basically, you can see all these signals are from the top surface of these grains, because only at this part the signal is the sample is at exactly 70 degrees, which is perfect for EBSD, for the electron to be reflected back to the detector. And also another example is on the right side. So this is from yellow phase cesium lab bromide. And you can see in the middle there is a very clear light blue color grain, which is a triangle gray in the center of SEM. And this is also the perfect end goal area for the measurement. So for making really nice measurement on perovskite, you have to make sure the film is smooth enough. This is the second point. And then with when we can get a nice signal, we did a lot of analysis with EBSD. So in the first figure, you can see this is the original EBSD map. This is a MAPI film. So it's very stable. It's made by spin coating, and it's very stable. And you can see we can get almost the signals from everywhere. And then we can define the green boundaries by calculating the misorientation between two grains. Let's say if we define when the misorientation is higher than a specific angle, we can say this is a green boundary. And then we can draw all the green boundaries around this map, which is showing as a black lines in the second figure. And then with the help of these lines, we can say where is exactly one grain. Then we can define all the grains, and then we can also calculate the misorientation within one grain, which is shown in the third map. So you see, so basically the dark blue color means the lower misorientation within one grain, and a lighter color means high misorientation. And later we can link this to the strain inside the grains, and also link to the performance of the device. And so also we can calculate the misorientation angle between each grains, which is shown in the fourth figure. And another thing is interesting we found here is the subgrain and subboundary. Because of the high resolution of EBSD detector, so we can see the orientation within inside one small grain. So actually it's very interesting. So we found some subgrains. So basically within one grain there are two different orientation. You can see this in the first figure. There is a black line in the middle of this blue grain, and on top of this the orientation is a little bit lower than the orientation below this line. So by calculate the misorientation here, we can define this black line as a sub-green boundary. So this is something we can see from SEM. And also another thing is if we compare SEM image with the EBSD, we can see some grains in SEM are actually not one single grain. Actually, it has a few more different orientations within this one grain. This is also mentioned by Loretta. So for example, you look at this black arrow. So in SEM, we see two clear large grains, but actually in EBSD we see 4 different colors. So that basically means there are more orientations within this one grain. Then by matching the EBSD map with a PL map, we can we can draw a conclusion here. So you see some small grains actually have a higher PL intensity, but the large grains always show lower intensity. And if you compare the PL intensity with the grain misorientation within the grain spread, so we can see that there is actually a negative relation. So that basically means a larger grain normally has a higher strain, so it leads to a higher non-radiative recombination, which is bad for the material. So this is the work I've done with the EBSD. Thanks.
Thank you, Hong Yu, and thank you, Loretta. Hopefully you've seen a number of the different types of analysis and information we can get from EBSD. If you're interested in learning more about this, we have another webinar next month titled Advanced EBSD Data Processing, Selection, Validation, and Quantification. That'll be presented by my colleague Renee Duclos. You can register on our website. Thank you for attending, and we'll take a few questions. They can be submitted via the widget here. I'll take the first one here. There's a question asking, would cryo-cooling help to avoid beam damage of perovskites during analysis? I think the answer is yes, we think so, but we haven't validated that ourselves yet. But we have talked about that as a possibility. Loretta, are you able to see the questions? You see the one here that's directed to you?
Yes. Yes, so there is a question from Justin Axel that asks if we have investigated formaldehyde lead iodide-based perovskite. The reason is yes. So I've tried to measure the formaldehyde lead iodide. However, there are, at least in my experience, we had some issue with the conductivity of this particular sample, because the formaldehyde lead iodide can easily go back to the delta phase, so the yellow phase, which is the non-conductive one. And so we couldn't measure very well the sample because it was changing over time. But of course, if you, for example, investigate the formaldehyde cesium, then I would expect higher stability for sure, because normally when you introduce inorganic cation, you also have, in general, more stable perovskite. And that should be also more easy to measure with the EBSD. But definitely also the formaldehyde lead iodide is possible to measure. The only thing is, of course, take care of the phase stability of the perovskite, which is besides the measurement itself. And then there was a second question still from Justin, and it is about the PL and how it correlates with the presence of special grain boundaries in the film, and if we can see multiple phases forming upon annealing, for example. So I didn't do this type of experiment, so with by looking at special grain boundaries, so I cannot answer 100% this question. But for sure, if you have different phases, and these phases have different crystal structure, or if there is misorientation between those the grains with those crystal phases, you should be able to measure it with the with an appropriate resolution with the EBSD. And with the PL is a difficult question, how this would affect the PL, in the sense that most of the time we think that grain boundaries are not good for the perovskite, but we actually had also some, we did also some experiment, and it's not always the case. So it's something that needs to be measured to get an answer. And thank you for the question.
Loretta, do you mind taking the one? There's also one that says, what tools are used for the PL signal?
Yes. So the tool that we have used is it's a confocal microscope. So it's not cathodoluminescence. So what we did was to mark the grain that we looked at under the EBSD, so in the SCM, and then we moved the sample in our confocal microscope. We found back the marker on top of this grain, and we measured pixel by pixel the photoluminescence coming out from the sample. So it's not cathodoluminescence.
Okay, I'll take a couple more of them. There's one question asking, which is the good configuration of the EBSD detector for 3D analysis? I'm assuming by 3D analysis, this means, essentially automated serial sectioning in a focused ion beam. And so there's two different ways, I guess, to interpret configuration. Typically the spatial configuration, the positioning of the detector is the same as regular 2D analysis. It's positioned close to the sample, tilted to 70 degrees. And for the 3D serial sectioning, the sample, depending on which instrument is used, is either tilted or rotated, or leaves the same position to do the serial sectioning slicing, and then reposition for EBSD, and there's some alignments that go on between that. The other talk is, which configuration of the EBSD detector in terms of which type to use, a direct detector or, say a high-speed CMOS. I think that more depends on what you're looking for. If your 3D application requires, low beam dose analysis, then generally you'd want to use the Clarity type direct detector. If a material, if you're interested in the fastest removal, which is sometimes, or the fastest characterization, then sometimes a high-speed CMOS might be more appropriate, if your sample can handle those beam doses. There was also another question, have we measured relative strain with EBSD? Yes, there's an application which is typically called HR EBSD, or high angular resolution EBSD, where an EBSD pattern from a reference orientation is compared to the experimental pattern, the pattern we want to know the strain from, and the distortions between the reference pattern and the experimental pattern are analyzed to determine the strain between them. And so, the Clarity detector is really good for this because there are no phosphors, no lenses, no fiber optics or anything. So you have direct detection. So you really have high information transfer onto the sensor that improves the precision of that sort of a measurement. And then there's one question here: what is the typical working distance for an acquisition? That will often range more by the type of SEM that is being used and the geometry of those ports. I'd say anywhere between 5 to 20 millimeters. Typically for something like this, I use about 10 to 12 on my, I have a Thermo Fisher Teneo FEGSEM. That's the range I often use. And Loretta or Hung Yu, one more of what, maybe from your side, what's the pixel lateral resolution of your PL tool? Maybe Loretta, are you able to answer that one?
I can answer this one, I think. Okay. This is about 500 nanometers or so, roughly. Depends on the wavelength you're using for the excitation.
Thanks, Eric.
Yeah.
All right. With that, I'd like to thank Loretta, Hung Yu, and Eric for their participation in this joint webinar. It was very fun. Thank everyone for attending. We appreciate your interest. And if you have further questions, please don't hesitate to follow up. Thank you very much.
Thank you.
Thanks.